All right. So let's talk now about sugar ring systems. So let's take 6 carbon. So there's a 6 carbon. Let's do an aldehyde. H2OH. Right, left, right. Right. This is glucose, ABAA. This is D-glucose. And then we can fill in the hydrogens. Those blank lines are always hydrogens. It's going to get very messy to include them shortly. So these will get left off. But there's always a hydrogen opposite the OH on these drawings. I'm just going to leave them out for clarity here soon. Because sugars in the Fischer drawing are, well, indeed, when they are free and reactive, this is the form they take, the vast majority of the time in biology, they are not in an open chain form. What happens is we kind of tip it on its side. So rotate it over onto its side. You get a carbon aldehyde. And depending how you kind of turn the carbons around, you kind of get something that looks like this. They spiral around on each other. There's an up and a down as we tip it over on its side. That is what is up and down on each of these. 1, 2, 3, 4, 5, 6 carbons. All right. Well, we got the hydrogen down on 6. Let's follow here. So carbon 1, carbon 2, 3, 4, 5, and 6. Carbon 1, carbon 2, 3, 4, 5, and 6. So carbon 2 has an OH and a hydrogen. Well, anything that was on the right, like hold up your left hand with the back facing you. So your left hand, the back of your hand facing you, your thumb should be on the right. If you rotate your hand clockwise, your thumb moves down. And that's what happens to OH. That right OH just gets rotated down. That left hydrogen, it gets rotated up. Go to carbon 3. Well, that right hydrogen gets rotated down. You can use the blue filler for that. And that left OH on carbon 3 gets rotated up. So all we're doing is tipping the molecule sideways. Like stand a book on end and then tip it over. Everything falls over to the side. But the translation for it is that when we want to tip this over, which is the first step to making a ring, all the groups that used to be on the left are now on top. All of these groups that used to be left, they are now on the top as we go around. So, top. All the groups that used to be on the right, they end up on bottom. So as we go to carbon 4, well, its OH was on the right, so it ends up on bottom. And the hydrogen ends up on top. Carbon 5 had the OH on the right, so it ends up on the bottom. And the hydrogen ends up on the top. So this is the first step. To make a ring sugar, you have to spin the molecule around like this. Well, what ends up happening is I have an aldehyde and an alcohol. And if you remember the reactions that an aldehyde plus an alcohol can have, you can get a hemiacetal. Well, I have alcohols and I have aldehydes on a sugar. You can do an internal hemiacetal reaction. So the same molecule but two different functional groups on that molecule can react with each other. And so that is what's going to happen here to our ring system. Let's move this down. The net effect of all of this is that what are we going to make in the end? Well, one of the OHs is going to attack that aldehyde. Now I'll tell you, well, nature can do it in many different ways, and you are able to do many different alcohols from this sugar can attack that aldehyde. For our purposes in class, it is always the last chiral carbon's OH. In our case, that's going to be this one. This will go and attack that carbon, pushing out a double bond to make an alcohol. The net result of this is carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. The oxygen from carbon 5 bonded to carbon 1. And then the aldehyde is now an alcohol, and the hydrogen is still a hydrogen there. All of the other carbons, carbon 2, carbon 3, carbon 4, they don't change. So you still have your OH down on carbon 2 and the hydrogen up. You still have the OH up on carbon 3 and the hydrogen down. You still have the OH down on carbon 4 and the hydrogen up. Carbon 5, though, it had to twist a little bit to bring that alcohol around. It had to bring it up from below, and so that OH kind of twists that whole carbon around counterclockwise, and it ends up shoving carbon 6 up to do it. So carbon 6 still has all of its groups, but it ends up going above the molecule. Carbon 5 did have a hydrogen, and that is actually still there. It just got twisted around so that carbon 6 could move out of the way for the OH. We're going to give you a few simple rules to build these, but this is the idea of what's going on. This is a ring of D-glucose. When D-glucose is actually stored as starches, as glycosides and other things in the body, this is how it is constructed. It is in a ring. These hemiacetals are fairly common for sugars, same as hemiketals when we get to ketose sugars. So how do we know how to do this? How do we plot and create these? Let's go back real quick to the Fischer drawing. Let's make up our own pattern this time. Let's say, looks like that. Well, I am going to connect my last chiral carbon. So here's 1, here's 2, here's 3. There we go. This lower one. That OH was on the right. This is my last chiral carbon. If I try to count my carbons and oxygens that are going to make the ring, think about how we made this. The carbon with the aldehyde got attacked by that OH, and all the carbons in between them became part of the ring. So I would count just carbon 1, 2, 3, 4, 5, and eventually that oxygen, when I connect it, will be part of the ring. This is a 6-atom ring. A 6-atom ring here is called a pyranose, and it always has the same basic shape. It always looks like that. Carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. Because that last chiral OH was on the 5th carbon from the double bond oxygen, it will end up including all 5 of those carbons and the oxygen itself from the OH into a 6-atom ring. Pyranose rings always take this general shape. Then we just have to figure out for each carbon whether things went up or down. And so we build our general carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. Well, let's start with carbon 2. It had an OH on the left. Left things go up. Hydrogen go down. Carbon 3, it has an OH on the left. Left things go up. Carbon 4, it was on the left. Left things go up. And so I can figure out that, hey, how are these up and downs going to work? Well, just as before, we've got OH on one side, hydrogen on the other. OH on one side, hydrogen on the other. But determining whether it was up or down was looking at whether it was left or right in the Fischer diagram. Things on the right in the Fischer end up on bottom in the ring. Things on the left in the Fischer end up on top in the ring. Until we get to carbon 5, because that one had to move in order to form the ring. It had to twist. For that, there's a simple rule. D sugars have extra carbons go up. And so there's a carbon 6 down here. Carbon 6, because we were a D sugar, carbon 6 is going to go up. H2OH. If you have an L sugar, the extra carbons go down. And we'll draw one of those soon enough. But that is how we can tell what's going on with carbon 5. Because the OH got turned into the ring instead of up and down, whichever carbon that OH was attached to, we have to follow these extra rules. So the D sugars have the extra carbon go up. So everything past the last chiral carbon will go up. And that means there's a little hydrogen over here that's going down. What about carbon 1? Well, what was on carbon 1? Like, we can see it over here. Right? The whole idea is the aldehyde. The carbon with the aldehyde has a hydrogen and an oxygen. It's going to have a hydrogen and an OH once you make the ring. Well, the problem is which one goes up and which one goes down. There's going to be an up and there's going to be a down. And the truth is, it can be either. Now, it's a little hard to see until we have a model, but because there's no chirality to carbon 1 initially, when you connect the oxygen, depending which side you attack, it will create chirality. Because if we look at carbon 1 now, it has an oxygen, a carbon with OHs, and it will have one hydrogen and one OH. We went from a non-chiral to a chiral center at carbon 1. When you do that, you get to create both. So you could have the OH go up and the hydrogen down, or, I'll do this one in green, or you could have the OH down and the hydrogen up. Both of these are possible. Which happens is random. It's 50-50. If your OH goes up, you are a beta sugar. If your OH goes down, you are an alpha sugar. So let me do that. A beta sugar versus an alpha sugar. So when you have D-glucose form a ring, or any sugar, when you have a sugar form a ring, you can get the beta or the alpha version of that ring. And in fact, if you throw a ring sugar in water, hemiacetals can open and reclose. So if you put 100 beta sugars in, and you wait a little while, some of them will break open and then reconnect, and they have a 50-50 chance when they reconnect. So come back a day later, and you have a 50-50 mix of alpha and beta. They swap back and forth over time. But they make a difference at any given moment. For one, beta glucose is used for cellulose, for cell walls in plants, where alpha D-glucose and beta D-glucose. Alpha D-glucose is what we get when we eat starches. That is what we use to store glucose. And the only difference was whether it was up or down when it was connected. Alright, the answer finishes our introduction to the idea of a ring sugar.